Hey everyone, Mr. Lee here. In this video, we're going to start the momentum and impulse unit. Let's get started. Alright, so the first variable that I want to give you is the variable for momentum. M-O-M-E-N-T-U-M. Now the variable for momentum is the letter P, and it's a lowercase p because the uppercase P stands for power. Why is it the lowercase p? Well, there's a lot of theories, and one of the theories is back in the old days, just like the word pterodactyl, right? The p is silent. There was a p in front of momentum, but a lot of people got confused by it, so they just dropped the p but kept the variable, for physics equations. Now, how true is that story? That story has no historical accuracy at all. Not many people know why the variable for momentum is p, but some people think that it stands for perseverance or persistence. All right, the momentum variable is p, and it is mass times velocity. And momentum is a vector, okay, and so is velocity. Now, the units for momentum, nothing fancy. The units for mass is kilogram, and the units for velocity is meters per second. And so we just get kilograms, meters per second as your unit for momentum. Now, simply put, the definition of momentum is just an object that may or may not be moving, right? So if an object is moving, we say it has momentum. If an object is not moving, we say it has no momentum. Next, we have this idea called impulse. All right, now impulse is where things get a little bit tricky. Impulse is the change in momentum, so delta p. So we can write a object's momentum is m times delta v, or m times vf minus vo. Okay, and of course all of these are vectors. Okay, now you might be wondering, well, what can cause a change in momentum? And we're about to figure out exactly what causes a change in momentum. Next equation down. Impulse. The variable for impulse. Not only is it delta p, okay, which is impulse, but the variable for impulse itself is the capital J. Now you might be wondering, why is it J? Impulse starts with an I. Well, we can't use the letter I because in math, the letter I stands for imaginary numbers, and the capital I stands for current, as in electricity. And so the story goes, back in the old days, impulse was spelled with a J, but the J was silent, and so they just got rid of it because it just confused people. And of course, as you might know, that has no historical accuracies at all. And so we are stuck with the letter J for impulse. I have no clue why it's the letter J. But the formula for impulse actually comes from Newton's laws. If you remember, one of Newton's laws says an object in motion will stay in motion unless there is an outside force. And so here's a cool little trick that we're going to do. We're going to actually write that law down. An object in motion stays in motion unless acted on an outside force. Now you might be wondering, Mr. Lee, why did you write that law down? Well, here's something cool. Impulse actually comes from this law. And so what I'm going to do, and I do encourage you to do this as well, I'm going to write down the variables within that law. Because a lot of physics, the variables and the equations, they all make a sentence. So an object is just m. In motion, that'll be your initial velocity, stays in motion, final velocity, unless acted on an outside force, F. And so right there, we have all the variables that we need to figure out the equation for impulse. So let's take a little deeper dive. MVOVF, and so we can combine that, actually we already did up here, so we know that delta P is M times delta V, and then we get this J. So where is this F coming from? Where the F is that F, you might be wondering. Well, let's take a view at Newton's second law. So I'm gonna do a little detour. Those are my detour lines. All right, so my second law. Where's my second law? So we can say that force, and we'll be using this form a lot. Force is equal to mass times acceleration. Well, we can rewrite this formula to say mass times the change in velocity over the change in time. Okay, because that's what acceleration is. And just to show you how I substituted that, I'm going to put my substitution in parentheses. Okay, so that's my acceleration is equal to force. So what we can do is we see that up here in the numerator, I'm going to highlight this. In my numerator, we have m times delta v, right? So that's my change in momentum. So I'm going to isolate that by itself. I'm going to multiply both sides by delta t. So F times delta t is equal to m times delta v. All right, and there you go. M times delta v, this is equal to delta p, and all of this is equal to j, and j stands for impulse. So this is where our definition comes in. If a system, okay, if a system is in motion, it'll stay in that motion unless there is a outside force, and that force will just act on the object over a period of time. All right, so what is the formula for impulse? Well, we already know that the formula for momentum is kilogram meters per second, right? As mentioned above with the m, the delta v. And the units for force is newtons, and the units for time is seconds, Newton seconds. So there is no one equation, or excuse me, one unit for impulse or momentum. It comes in two forms: newtons per second, or Newton seconds, or kilograms meters per second. Either one is a-okay. You will see both the same amount. All right. So let's go. Let's create a little list of formulas that we are given. So the formulas that you will see on your equation sheet, okay, is the momentum equation. You will see this one. You will also see the impulse equation. Impulse, which is also a vector. I keep on forgetting my vector signs, and put that everywhere. Impulse is equal to force times the change in time, which is delta t, which is equal to delta p. All right. Now on your formula sheet, there's also a integral there. Okay, and we're going to go into exactly why. So these two equations right there, that will be found on your equation sheet. The third equation that you will find on your equation sheet, it comes from this equation. So we're about to derive that. All right, so I'm going to write that second equation down below here. So we have F equals ma, and from there we know that this can be m times delta v over delta t. Okay, and we know that m times delta v is just the change in momentum over the change in time. Okay, so we can say force is equal to delta p over delta t. And I do believe the story goes that Isaac Newton first wrote the second law in this fashion. I think that's how the story goes. Okay, so the change in momentum over the change in time is equal to the force. All right, so these three will be found on your formula sheet. This third equation, you will see it written like so. Instead of delta p written like that, you will see it written as dp over dt. All right, so these three will be found on your equation sheet. Okay, now let's get into a little bit more of the calculus behind all of this. I'm going to use this second equation for all of my explanations. So if you were given, so I'm going to write this equation up here, f dot dt, it's not a dot, it's just f times dt, it's not a dot product, is equal to delta p. All right, so if given a force function with respect to time, okay, I'm going to say it again, if given a force function with respect to time, you can integrate, okay, and that's where that integral symbol comes from, right there, from time initial to time final. So those are your constraints. So this will be time initial here, and this will be your time final up there, to find impulse. Okay, so if you're given a force function with respect to time, you can integrate it to find the impulse. Now, with that being said, if we take a look at this equation, this third equation right here, I'm going to write that out for our sake, dp over dt. So this one states, if given a momentum equation, a momentum function with respect to time, you can, that should be a C, you can take the derivative to find the force. Okay, Okay, so keep these two in mind. If you're not too savvy with the calculus, as long as you have this down in your notes, you can probably solve any and all the problems pretty easily. All right. So what does this mean? What does all of this mean? What is impulse? So simply put, Newton said that if an object is moving, it'll keep on moving, right? If you get an object and you hurtle it in space and there's nothing around, that object will keep on moving for an infinite amount of time, unless there's an outside force. And so the idea behind momentum is just that. It's just an object that is moving. All right. Now, the reason why this is so important is because now we're taking a look at the system for objects, a system of particles, and how forces affect the system. And so even though the momentum equation is pretty simple, right, just m times v, we can apply so many different little aspects of physics to see exactly how the universe interacts with each other from a very small atomic scale to a grand macro scale. Really cool stuff. Okay. So a couple of other things I want to focus on with this form of the equation, right? So if you're given f dot dt is equal to delta p, okay? If we take a look here, this is the integral of a force function with respect to time. So in terms of a graph, what this means is that we have a force times time graph, and let's say you are given a curve that looks like this, whatever that curve is. Because we're taking the integral, that integral states that the area under the curve, so let's say this is t initial and this is t final, this area under the curve right there, that would represent your impulse. Okay, so that's how much your momentum changes by. That is your delta p. Now, the cool trick there is if that is your area under the curve, you can set that equal to mvf minus mvo, and depending on what the problem gives you, you can probably solve for another unknown variable. All right. Another trick that I like to think about, if the whole idea of the integration is not your strongest suit, is we're multiplying the y-axis with the x-axis, right? We're multiplying the two together, and whenever you multiply the two variables together, you will always be looking for the area under the curve. All right. A little side note. So this is if an object does not lose mass and it is moving, right? An object in motion stays in motion. However, we haven't talked about what if the object is in motion but it's losing some of its mass. And an example of this would be a rocket launch. So as a rocket is launching, right, just do a little quick little sketch, right? So we have a rocket, and then we have my explosion. Right, throw some orange flames, some yellow flames, right, and then we have some of the rocket little, I don't know what those are called, steering things, right? And this rocket, pew, it goes out in space. And so in order for this rocket to be expelling all that fuel, it's losing a lot of mass in order for these explosions to be created. And so in terms of this, we can actually use the momentum equation to find out how does that loss of mass affect the system or the object's momentum. Okay, so let's start off with the equation F is equal to the change in momentum over the change in time. Okay, so how is this momentum changing over a period of time if the object is losing some of its mass? So we can rewrite this as d momentum is mass times velocity over the change in time. Now here's a cool little calculus trick that we can do. If we have a derivative of both mass and velocity, we can write it like this. The derivative, the change in the velocity with a constant mass over a change in time, plus the object's velocity for a specific change in the mass over a very specific unit of time. And that will give you the force. So this right here, my friends, this is the equation for a object's changing in mass, okay, such as a rocket. And so we can say that this is in fact rocket science. Pretty cool stuff. This equation is not on the equation sheet. It's just a cool little tidbit. I don't think you actually need it. I haven't really seen it before, but it is there just in case you need it. So this is an object where it's losing a lot of mass, but its momentum is constantly changing. All right. The last thing I want to end with is the relationship between the variables for impulse. Okay, so we're going to come up with different scenarios. Let's say let's see. So we know that impulse is equal to delta p, which is equal to force times delta t, right? And we got some vectors up there. All right, so let's say we have two scenarios. We have, we'll have an egg, okay? So we'll have an egg, and in scenario 1, this egg falls on a brick, red brick, all right? And in scenario 2, this egg falls on a pillow. All right, it's a lumpy pillow. All right, so scenario 1, it falls on a brick. In scenario 2, it falls on a pillow. All right, so here we have a really cool scenario. So this object will fall, and right before it hits a brick, we're going to say that this object has a velocity, initial velocity. What is it? I don't know. Same with this object, because both objects are being dropped from the same height. This object will fall, and it's going to hit the pillow at the same height or the same level as the brick, and we can say that it also has the same velocity. Okay, so for here, we can say both eggs will hit the object with the same velocity. Okay. All right, so both objects will hit the both eggs will hit the object with the same velocity. Now, there's going to be a big major difference. We're not going to get into if the egg survives or not, but the big major difference, well, that is actually the big major difference. But another thing that we should talk about is the final velocity. We will say that they both have, well, there's going to be a final velocity for both of them as well. All right, so they both share a VF of 0. All right, because they both come to rest. All right. And both objects will come to rest. So the question is, why does the egg break on the brick but survive, hopefully, on the pillow? Now, if we take a look at the equation, this equation tells us everything. So we can say that because both of the, all of the conditions are basically the same, right? The initial velocity is the same, the final velocity is the same. We can say that the delta P for the brick and the pillow is the same for both, all right? But let's take a look at the other side, where we have force and we have the change in the time. So let's think about this. In which scenario is there a greater force, the brick or the pillow? Acting on the egg. And so when we think about that, let's just think about the egg survivability. When the egg hits the brick, it's going to experience a lot of force. Now, why can we say this? Why can we say that the egg on the brick will have a greater amount of force? Well, simply put, the contact time, okay, that the brick makes with the egg is very, very, very short. Okay, the egg will hit the brick, and that's it. Like that instant that it hits it, that's all the time that it needs. All right. Compared to the pillow, when the egg hits the pillow, the egg will not only hit the pillow, but it'll continue moving into the pillow. Okay. And so notice how I'm phrasing that. It'll hit the pillow and it'll keep on going into the pillow. So that's a longer period of time. And so for here, we can say that this is for the brick. There's a great force because there's a very short amount of time that the brick is in contact with the egg. However, with the pillow, we can say that the egg is in a greater contact time with the egg. Okay, so because the egg is in a greater contact time with the pillow, the amount of force, the overall force that the egg experiences will go down, and therefore the egg will survive while hitting a pillow. Now, this is also true a lot of times for different things like sports, but I'm going to go into car science here because this is exactly what happens with during a car accident. Now, it kind of really sucks to talk about, but thank goodness for physics and for technology because it's basically life or death. So let's replace the egg with like your skull. Okay, so let's say we get into a car accident, and as soon as your car gets into an accident, remember an object in motion stays in motion, so even though your car's coming to a stop, your body is still in motion. And luckily you have your seatbelt on, and so your seatbelt will prevent you from moving forward, but your head's not strapped in, so your head will continue moving forward, right? An object in motion stays in motion. So if you're moving 35 miles per hour and you hit a, I don't know, you hit a wall or something, or you hit another car, even though your car comes to a stop, your head will still move forward at that velocity. Okay, so that's the backstory. I just described what it's like to get into a car accident. Here's our steering wheel. Okay, usually with the steering wheel, the airbag deploys. Right, airbag deploys in your face. It hits the airbag. That's my face of a person getting into a car accident, right? And what the airbag does, the airbag increases the time it takes for your head to come to a stop. And that's important. It increases the time it takes for the head to come to a stop. And so the force that your head experiences is overall less compared to, it's going to still hurt. If you ever got an airbag blown up in your face, one time I did, and my nose, it felt like I got punched in the face. My nose started bleeding. But let's say that airbag did not deploy. This is not good. Let's say the airbag does not deploy. Okay? And instead, your head goes boop, and it hits your steering wheel. Oh no, right? So your head here hits that steering wheel. Now the contact time that your face is in with the steering wheel is very short. So this is steering wheel. The contact time that it takes for your steering wheel is very short. And therefore, the force that your skull experiences is very big. And that's major ouchies. I would rather take a collision with a airbag than the steering wheel. All right. Now another case that we can take a look at, and this one's a little bit trickier, but the math does check out. But this is a classic physics problem. All right. The question is, which scenario has a greater impulse? Okay, and remember, impulse simply means a change in momentum. So this is a classic one. I'm gonna copy this down. I wouldn't even remember it. I will memorize how to do it. So let's say scenario one, we have a particle is moving forward with a velocity of v. Okay, let's say this is I think they usually call this the clay ball, right? Kind of like a Play-Doh. It hits the wall, right? And then after a period of time, the clay comes to a complete stop. Okay, and the clay kind of just like gets smushed into the wall. So that's my clay, right? So initial velocity, we can say it's v. Our final velocity, we can say it's 0. All right. Now a different scenario, it'll be the same kind of thing, except it's not a clay ball. Let's say it's a metal sphere or a bouncy ball, metal or rubber, right? Anything that can bounce. All right, it's moving forward with a velocity of v, pew, right? And then it collides into this wall, all right? And after it collides with the wall, it bounces back. So we can say that initially it was going, let me draw the arrow a little bit better. Initially it was going to the right, and after the collision, we can say it bounces backwards. All right, Vf is equal to negative V. Now, they will always present you the scenario like this. One comes to a complete stop, and one is just bouncing off. So a lot of students believe, and you can check your own beliefs, which one has a greater impulse, which one has a greater change in momentum, that because this comes to a complete stop, this has the greater impulse. And a lot of students believe, well, it's still moving. Momentum is an object in motion, and it will stay in motion. Therefore, this one, the momentum didn't change at all. Let's see what we can find out mathematically. So we know impulse is delta p is equal to force times the change in time. Okay. Now, what I want to focus on is this left-hand side. So let's say that for both objects, they have the same mass. All right. So m vf minus vo is equal to impulse j. We want to focus on the impulse. We know that the final velocity is 0. So 0 minus vo is equal to j. So our impulse is equal to negative mvo. Okay, it changed by that amount. That is how much the momentum has changed. Now let's compare that to this one. Delta p is equal to f times delta t. We can say that it's mvf minus vo is equal to j. We know that our final velocity, okay, and this is the part that a lot of students forget, so I'm going to put this as a red flag moment. Okay, this is the key to solving this problem. Because it's moving to the left, it has negative velocity compared to the initial, where it's moving to the right. Okay, minus your initial positive, so that's just minus m minus v. And so we get m times negative 2v is equal to j, and we can say negative 2 mv is equal to the impulse. And so if we take a look here, this is the one where it comes to a complete stop, and this is the one where it bounces. We can say the greater impulse is the bounce. It's a greater impulse. In fact, it's 2 times as big. It has twice the impulse. And that is because of that bouncing off motion. And so if we were to think about this in terms of forces, remember because it's force times time, the way that we can think about this first scenario here, up here, is if a object is coming into collision, okay, it's coming into collision with the wall. For this one, as it comes to like a splatting motion, we can say the force just needs to stop the ball or the clay ball. Okay, as it's like hitting the wall, all the wall has to do is bring this clay ball to a stop. But for the bouncing one, okay, so for the bouncing one, I don't know if you've seen those slow-mo videos, but it's really, really cool. This is like a baseball bat or so this scenario would be like a baseball bat or like a tennis racket. Okay, so as the ball is hitting the surface, it not only splats, this is what I mean by it's really cool to see, the ball actually deforms a little bit. If you want to look up slow-mo videos of golf balls kind of deform like this, baseballs deform like this, tennis balls definitely deform like this. Okay, not only has to deform, but the ball has to be, so this here, the velocity is here, so it deforms, velocity here is 0, okay, but it also has to push it backwards. So for this scenario, the wall has multiple jobs. The wall has to bring the ball to complete rest, and that's the key part, and the wall has to push the ball backwards or against its initial motion, right? Because that's what we call it, rebound, right? It has to bounce backwards. All right, so if we were to compare, right, so the first one, all the wall has to do is to bring it to a complete stop. And for this one, it has a lot more to do. Not only does the wall have to bring the ball to a complete stop, but it also has to bounce it off in the opposite direction. Okay, it has a lot more to do. And so here in sports, right, there's a lot of sports with impulse and momentum. I try to tie it one more time. If you catch a ball, so if a ball is coming towards you and you're trying to catch it, this is what we call cradling the ball, okay, or you're moving with the ball. So if the ball is coming and you're trying to catch it, so as the ball hits your hand kind of moves with the ball, and so you're decreasing the force it takes to hit your hand by increasing the slowing down time. So if you cradle the ball, F times delta t, as the ball hits your hand, you're going to move with the ball, so you're increasing the stopping time. That means that there's less force on your hands, right, and less force on the ball. Because more force on the ball means that the ball will probably bounce out. Versus this one, when the ball comes and you don't cradle it, you just kind of have like stiff hands, and the ball just hits your hands, right? In this case, because the ball just hits your hands and your hand doesn't like give into the ball or cradle it, the time it takes for the ball to make contact with your hands decreases significantly, and so the force that the ball experiences, and also your hands will probably hurt if you catch a ball this way, will go up, and it'll be, ouchie time. Okay, and so this is if it bounces off your hands, versus this one if you successfully catch it, right? Okay, well, let's just do a zoom out view. That's my favorite part. Wow, we sure did learn a lot today. So as a reminder, for impulse, okay, if it rebounds, there's always going to be a greater impulse. The equation for impulse, it is determined on force and time, okay, is a function of force and time compared to energy. Okay, trying to bring it all together. Energy was a function of force and position. So be careful, be very, very careful. You know what? You have to be so careful that I'm going to write it down. All right. So momentum is force and time. time dependent, or delta P, okay, and the change in energy is force and position dependent, okay. Very, very similar, not the same. So when you're given a function, keep an eye out. All right, keep an eye out. Let's red flag this one. All right, keep an eye out for that. We also learned if you're given a different type of function, how that function, or how we can use calculus to find out different things about the function. All right, so that's impulse in a nutshell. I'll see you next time. Bye-bye.